Picture a classic geometry puzzle, the kind that looks incredibly innocent on a whiteboard until you actually try to solve it. We're handed a quadrilateral, ABCD, split right down the middle by a diagonal, BD. At first glance, it feels like an information overload. We know vertex is precisely 68 degrees, flanked by a 35-degree and a 77-degree angle inside that left triangle, and just across the fence, we're given a 37-degree angle at vertex B. Our mission is to find the missing angle, BDC. But here's the kicker. If you try to solve this using basic middle school angle chasing, you'll find yourself running in circles. There just isn't enough rigid structure. That is, until the problem drops one final, crucial constraint. The boundary segments AD and BC are perfectly equal in length. Suddenly, what looked like a loose, shifting shape locks rigidly into a single, beautiful solution. So how do we crack it? Since we can't rely on simple subtraction, we have to bring out the heavy machinery of trigonometry, the law of sines. The trick to bridging these two separate triangles is using that shared diagonal BD as our baseline scale. In the left triangle, ABD, we know every single angle, which means we can cleanly express the length of side AD strictly in terms of BD and the sines of its angles. Then, we jump across the diagonal to triangle BCD. We don't know our target angle, so we call it X, making the final angle 143 degrees minus X. Applying the law of sines a second time allows us to right side BC in terms of BD and our unknown variable. Because the problem guaranteed us that AD equals BC, we can set these two mathematical expressions face to face and watch the baseline BD entirely vanish from the equation. What we're left with is an elegant algebraic tug-of-war. The ratio of sine of 35 degrees to sine of 68 degrees must exactly match the ratio of sine of x to sine of 143 degrees minus x. By expanding that denominator using the sine addition formula and converting the expression into cotangents, the hidden geometry finally unravels. When you run the numbers through the arithmetic crucible, the target angle x separates itself from the noise, yielding a precise, locked-in measurement of approximately 36.35 degrees. It's a spectacular reminder of why geometry is so captivating. A single constraint, an equal sign between two distant sides, completely transforms a fluid puzzle into an absolute mathematical certainty.